Okay, so a big welcome to everyone. I am Sandra Di Rocco, the current chair of SIAM activity group in algebraic geometry. And I welcome everyone to this grand opening of our seminar series in applied algebraic geometry with acronym SAGA. We are very happy to start with a great friend of SIAM, Rekha Thomas. Rekha has been a plenary speaker in both the SIAM conference in optimization and the SIAM conference in applied algebraic geometry. And it will be a great pleasure today to listen to Rekha telling us about when two cameras meet a cubic surface. So please, Rekha, and thank you.
Thank you, Sandra. And thank you for everyone who's here. So my talk today is about reconstructing three-dimensional scenes from pictures from two-dimensional pictures. And this is, as many of you know already, this is a very foundational problem in computer vision. It's a geometric problem and it has a very long history. And I will talk about a particular question that arises in this situation. So this is joint work with several people. So here are my collaborators, Sameer Agarwal, who's at Google here in Seattle, Andrew Pryhuber, who's a joint student of Sameer and mine. He's finishing his PhD at the University of Washington, and Rainer Sinn from the University of Leipzig. Okay, so let me start by telling you what the main question is that we worked on. So what we're given are two sets of points in the plane. Okay, so there are these U points, U1 through UK in general, and there are V points, V1 through VK in general. So we're given these K point pairs, UI, VI, they are in R2 cross R2. And the question is, when are these images of K points in the world, in our three-dimensional world, in two cameras? This is the question. Okay, so it's a very, very basic question in vision. And we want to know if there are constraints on these points. Can you arbitrarily throw K points on one side and K points on the other side and hope to reconstruct them in the sense of finding K three-dimensional points that will image to these two particular U's and V's under two cameras? So, okay, this is the question. So to answer this question, first of all, you have to figure out what your model of cameras is. You have to fix some model. So cameras in general are just maps that go from R3 to R2. So you can have complicated maps. But for the purposes of this talk, we will consider like the most basic model of cameras, which are projective cameras. Okay, so this is a generalization of the usual pinhole camera. So let me just go through the basics of it because this is important. So a projective camera, this is the affine picture of it. What it is basically two components. It has this viewing plane, which is given by this blue rectangle here. And it has a center, which is a point in 3 space. And if you want to take a picture of a world point, which let's call it Q, so this is a point in R3, what you do is you draw the line segment that joins Q to the center. You look at where it intersects the viewing plane, and that point U, let's call it U, is called the image of Q. Okay, so this is how you take a picture. And I've also drawn this pink ray here, which is called the principal ray of the camera. This is just the perpendicular from the center to the viewing plane. And this principal ray has an arrow. And as you might see from this picture, there is a front for the camera. So if you want to take pictures of world points, these world points have to be in front of the camera in reality. They cannot be behind the camera. And that's what this principal ray is going to help us do. It's going to identify what we mean by the front of the camera. Okay, so let me write this mathematically now. So the picture below is in R3. But the typical model is to bump this all up into projective space. So a camera is a map, which I will call A, from P3 to P2. It's a rational map. And it'll send a point Q in P3 to A times Q, which is the image, which we call U. Okay, so this is defined everywhere except in one point, which I will talk about in a minute. So it's a rational map. And the matrix A that defines this linear map is just some 3x4 matrix that we fix up front. It's only defined up to scale, but we're going to just write down a particular representative, and it has to have rank 3. Otherwise, it'll collapse the world onto a line or a point, which we don't want to do. Okay, so this is what a camera is. It's just a matrix, 3x4, rank 3, and it defines this linear map. The center of the camera you can calculate once you have this map. So that's just going to be the unique right kernel element of this 3x4 matrix. So this 3x4 matrix has rank 3. So there's a unique C that's in the right kernel. That's the center. And we call the camera finite if and only if the center is a finite point in P3. Okay, so this is these are some basic definitions. And the principal ray is some vector. So I'm going to call it N. And again, everything is bumped up into P3. So these things also live in P3. So these are the basic constructs that we need from the camera. So we're going to use cameras like these. These are called general projective cameras, and answer the question that we had before. All right, so let me define what it means to actually reconstruct. So what we're given is these collections of points, UI and VI. There are K of them. They're paired up. And as before, we're going to bump everything up into projective space. So I'm going to put a 1 at the bottom of the two-dimensional points we had before and put these into projective space. So they live in P2 cross P2, but over the reals. Okay, so this is our input. I'm going to call the script P, and this P will happen throughout the talk. This is the set of point pairs that we wish to reconstruct. All right, so here's the first type of reconstruction you can do. You can do what's called a projective reconstruction. And a projective reconstruction just means the following. I need to find two cameras, A1 and A2, projective cameras, and world points, which we're going to collect into this big Q. So it's a set of points Q1 through QK. They live in P3. And they must image to these U's and V's. So in other words, when I apply camera 1, A1 to QI, I should get UI. And when I take A2 times QI, I should get VI. And the squiggle here, this tilde here is just meaning equality in projective space. That's all. Okay. So these are algebraic conditions, and a projective reconstruction simply means to find an A1 and an A2, two 3x4 matrices, world points which live in P3 that satisfy these linear equations. Okay, so that's a projective reconstruction. And these have been studied extensively. And for two cameras, we pretty much know everything about these types of reconstructions. But as I just mentioned before, these reconstructions are not exactly correct because they can reconstruct points that are not in front of the camera. So what we actually want is what's called a chiral reconstruction. So chiral for sign in some sense. And informally, what this means is that we want the world points to be in front of cameras, not behind cameras. And that in turn is guaranteed by satisfying a bunch of inequalities. So I will have a bunch of inequalities that are given in terms of the principal rays of my two cameras. So N1 is the principal ray of camera 1, N2 is the principal ray of camera 2, and I need to satisfy these quadratic inequalities for every QI, and also some more inequalities where N infinity is the normal of the plane at infinity. Okay, so the plane at infinity in P3, we assume we fix its normal to be just 0, 0, 0, 1, the fourth unit vector. And so there's all these inequalities that need to get satisfied to actually get a chiral reconstruction. So this is one that's truly a real physical reconstruction, not just one that is satisfies these algebraic conditions. So you see there are these algebraic conditions and these semi-algebraic conditions that need to be satisfied. And these type of reconstructions are much less studied. Okay, so For 2 cameras, chirality was studied in the 90s and the early 2000s. I'll say a little bit about its history, but this is the type of reconstruction we want. All right, so let me show you a picture of what the difference is. So on the left here, you see a comb, and on the right, you see a projective reconstruction that is not chiral. Okay, so it satisfies all the algebraic equations, this weird looking thing, but it does not put the comb in front of the camera. So it splits the image across the plane at infinity. And this is the kind of reconstruction we do not want. Okay, so this is projective, but not chiral. This picture is from the very nice book of Hartley and Sisselman, which is sort of the standard reference for all of these geometric problems in computer vision. Okay, so we want chiral reconstructions, not just projective reconstructions. And chirality was studied in the 90s by Hartley, especially for 2 cameras, mostly for 2 cameras. And he has some very nice results. And then also further studied by Thomas Werner, Tomasz Pajdla, and several others, mostly for 2 cameras. And in the first paper we wrote earlier this year, we generalized chirality to multi-dimensions, or multi-dimensions meaning multiple cameras. And then in the second paper, which is what I'm talking about, we are focusing on 2 cameras. Okay, so this is a picture of a projective but not chiral reconstruction. All right, let me also pause for a moment to just talk a little bit about the history of these problems. So these problems are very old in some sense. And here, for instance, is a problem that was raised by Chiral, the French mathematician Chiral, in 1855. So he asked the following question. So if you're given 7 point pairs, UI and VI, which are known to be images of 7 world points in 2 projective cameras, he wanted to show that, he asked whether you can show that there exists at most 3 projective reconstructions up to P3 automorphisms. Okay, so this question is from 1855. It was solved by Hesse in 1863. Okay, so these problems have been around for a long time. It's not exactly our problem, but it's a very closely related problem. And in fact, for practical reasons, this was studied also from the mid-1800s in what's called photogrammetry, which is the science of understanding 3D objects from photos. So if you have aerial pictures of a terrain, you want to create topographic maps, or you want to make measurements, you want to do land surveys, it's used extensively in archaeology and so on. Okay, so these are very, very old questions that come from projective geometry and had very practical applications. And our question sort of fits in this general framework of understanding reconstructions. All right, so let me go to the situation of 2 cameras and our question. So if you have 2 cameras, so let's say we have a camera A1 with center C1 and a camera A2 with center C2, and I take a picture of this world point Q, then this Q images to U in the first camera and to V in the second camera. And this orange line you see at the bottom is called the baseline of the camera pair. So it is the line that joins the 2 centers. And you notice that this baseline intersects the 2 cameras at 2 special points called E1 and E2. So E1 is the image of the center C2 in the camera A1, and E2 is the image of the center C1 in the camera A2. Okay, so these are very special points. They're called the epipoles of the camera. And the key thing you notice is that if you give me Q and one image, I cannot put the other image wherever I want. The other image is constrained to lie on this plane, right? There is a plane that's hinged on the baseline and contains Q. This is called the Epipolar Plane. So there is an algebraic condition that connects this U to this V. Okay, so this is an important constraint. And the way you write this mathematically is like this. You say you can express this planarity by saying there exists a X, which is a 3 by 3 matrix. It's real. It's only defined up to scale, but it's real. It has to have rank 2, and it has to satisfy this equation. So V transpose times X times U has to be 0. So the U and the V are linked together through this matrix called X. This is called the fundamental matrix of this reconstruction, or these cameras. And this constraint is exactly the same as saying that all of these things lie on a plane. Okay, so we're going to be working with these X's rather than with cameras. So let me actually show you how these things all relate with each other. So if I have two cameras in a projective reconstruction, then that carries, these two cameras uniquely define a fundamental matrix. So there is an X that we can construct from the two cameras. It'll be 3 by 3. It'll have rank, it'll be 3 by 3. It has rank 2. It's real. And it satisfies all of these equations that we had on the previous slide. So for every one of the points ui, vi, it'll satisfy this equation vi transpose times x times ui is equal to 0. And these are called the epipolar equations of the point pairs. Okay, so there is this world of fundamental matrices. They live in 3 by 3 space, which of course is isomorphic to P8. If you just concatenate the rows of the matrix into a long vector, then I can think of P3 by 3 as just P8. And we'll do that in this talk. So these matrices live in P8, if you like, and they carry the same information as the cameras. But then there's also a third object that carries the same information, which is the right and left kernel of this matrix X. So this matrix X is rank 2. So it has a unique right kernel and a unique left kernel. And they turn out to be exactly the epipoles of the cameras. So there is this epipole space, which is P2 cross P2, right? Because the camera is 3 by 3, so E1 and E2 are both points in P2. So there is an equivalent story that goes on in P2 cross P2, one that goes on in P8, and that one that goes on in camera space. So we have all these three worlds in which we can ask the question or work in. And this talk is mostly going to be focused on the bottom two spaces in P8 and P2 cross P2. Okay, so these are what these fundamental matrices are. They are essentially equivalent information to the cameras. Okay, so what does chirality mean in these three different worlds? So in the first world of cameras, we saw that chirality is given by these inequalities involving principal rays. You can translate those inequalities into fundamental matrix space, in which case they end up being polynomial inequalities that are indexed by I and j lying between 1 through k. So there is a gi and a gj. Gi corresponds to the point pair with index I, and gj to the point pair with index j. They turn out to be high degree polynomials. These are degree 6 polynomials in the entries of X. They live in P8. And in epipole space, if you translate what these inequalities mean, you end up with an oriented matroid check. So in P2 cross P2, we have to check certain signs. It turns out to be checking the equality of two partial oriented matroids. And I'll just be vague about these, but the main point is that all of the chirality inequalities that we had in the beginning have translations into these two spaces, which are P8 and P2 cross P2. Okay, so once we have this, we can actually start converting all of this into geometry and see how we can check if there are chiral reconstructions. So let me do this slowly. So I want to start by translating what it means to be a fundamental matrix. So let's take X, fundamental matrix. And remember, this matrix has rank 2. So what I'm going to do is I'm going to start with just the space of rank 2, of matrices of rank at most 2 of size 3 by 3. So this is now in complex space. Okay, so we really care about real things, but because everything is easier to set up, we're going to start in complex space. So I have R2, which is the set of all 3 by 3 matrices of rank at most 2. This is a hypersurface in P8 with one equation determined in X equal to 0. It has degree 3. To be a fundamental matrix, you also need to satisfy these epipolar equations. So we have a plane, which is codimension k. There are k of these equations. So generically, it's codimension k. This is a plane in P8. And to be a fundamental matrix, you need to be in the intersection of both. So you need to be in R2 and you need to be on this plane LP. So we're cutting R2 with this plane, but you need more. You need to be in the real part of this, and you also need to be exactly rank 2. Okay, so you cannot be a rank 1 matrix inside this. So this complex variety, which is R2 intersect LP, is called the epipolar variety of P. But inside that, we need to be in a subset to actually be a fundamental matrix. So that's the first piece of geometry that goes with this. Okay, so the next thing we need are something that I'm going to call walls and corners. We'll see later why this plays a big role. So I'm going to let W of UI be all the matrices X that have UI as its right kernel. Okay, so this is a subspace. And then we're going to intersect that with the plane that we already had, which is LP, given by the epipolar equations. So this is some subspace of P8. It has codimension K plus 2. So it has 2 additional independent equations to the ones in LP. And similarly, we have another subspace, which I'll call W to the VJ, which are all the matrices that have left kernel VJ. Okay, so these are both subspaces. They have codimension K plus 2. And we'll call these walls. So this is the UI wall, and this is the VJ wall. So they have one more codimension than the codimension of the epipolar variety. Okay, so that's why we'll call them walls. And then sometimes we're interested in, or oftentimes we're interested in their intersection. So if I intersect the I wall with the J wall, I will call the intersection a corner. So we're going to call this the UI VJ corner. This is also a subspace, and it has codimension 1 more. So it has codimension K plus 3. Okay. So to be truly a fundamental matrix that corresponds to a reconstruction, there is a subtlety, but that I'm not going to really talk about. But what is important is that if you take an I corner, if you take an II corner, meaning the intersection of the UI wall and the VI wall, then the fundamental matrix can either be in that corner or it has to be off of all the walls. Okay, so there is this extra little complication which we won't really talk about, but the walls and the corners will come up again later. Okay, so that's also important in the reconstruction. So let me do an example just to see what all of these objects look like so far. So let's take the case of K equals 5. So I have 5 point pairs in both sides. So in this case, the plane that's given by the epipolar equations, this has 5 equations in it, right? It has 5 epipolar equations. So generically, this is codimension 5 in P8, which means that it's isomorphic to P3. So this plane is isomorphic to P3, all right? And now we're intersecting this plane with the cubic surface, with the determinantal hypersurface. And when you do that, you end up with a cubic surface in P3, right? Because I have a 3-dimensional plane and I'm cutting it with det x equal to 0. So I have a cubic surface in P3. So here's a picture of one. And this is what the epipolar variety looks like for K equals 5. It's a cubic surface. The walls that we saw before, WUI and WVJ, these are lines on the surface. They have 1 more codimension than the epipolar variety. And because I had 5 points and 5 points on the other side, I will get 10 real lines from these walls. Okay, so this surface, we will see in the end, has 27 real lines, but 10 of these lines come from these data points that we started with. Now, a key fact for us is that these inequalities that we need to satisfy, they're complicated, but the real zeros lie exactly on these walls. So if I look at where GI and GJ vanish on a fundamental matrix, that's exactly when the fundamental matrix lies on the I walls and the J walls. Okay. So the chiral region that we're looking for, meaning the set of fundamental matrices which live on this cubic surface that we care about, have to lie in this some semi-algebraic region that's going to be cut out by the inequalities, along with that regularity condition that I did not really explain, but it's a complicated set that lives on this cubic surface. Okay, so that's the set we're looking for. So this is an example just to give you a sense of what these geometric objects are. So what we need, where we are at this point is we can conclude now that P has a chiral reconstruction if and only if this chiral region is non-empty, right? So on this cubic surface, which is for k equals 5, but in general, there is some semi-algebraic set. That set has to be non-empty. And if that's the case, there's a chiral reconstruction, and it has a lot of pieces to it, like real, rank 2, it has to be regular, it has to be satisfy these inequalities and so on. So it looks pretty complicated, but that's the fact of life. Okay, so this is chiral, there's a chiral reconstruction if and only if this region is non-empty. So let me show you 2 examples, and these examples will show up again. So here's an example where I fixed the left image to be these U points. So these are very exactly embedded. This is not a random drawing. So I take these 5 points embedded exactly like this. And if in the right image, I take these green points, I will get a chiral reconstruction. Whereas if I change the green point slightly by moving this 0.5 to the other side, so the 0.5 flipped from down here to up here, then suddenly there is no more chiral reconstruction, okay? So these are 2 examples that we will see again in a few minutes. And it just gives you an example of the type of what actually happens in the case of k equals 5. And I will try to explain why and how we know these results. Okay, so technically speaking, we have to test the non-emptiness of some semi-algebraic region, but it turns out that the tests that we are actually able to devise are a lot more simple and nice. So that's where we're headed. Okay, so let me state the main results now. So the main results we prove are the following, which is in a certain view of the world, a complete answer to the question. So our input is these point pairs, ui, vi, k of them. And the first result we prove is that if k is at most 3, so if you only give me 3 points on each side, then there's always a chiral reconstruction. This is unconditional. Okay, so I don't care what the geometry of the points look like, I will always be able to chirally reconstruct. But on the other hand, if k is greater or equal to 5, then P may fail to have a chiral reconstruction, even if the U's and the V's are in general position. Okay, so this example we just saw in the previous slide, this example is an example of a situation where the 2 sides, the points are in general position, but at least this one is, but there can be no chiral reconstruction. Okay, so we'll see that example again. So it seems like from 5 onwards, there is no hope, and k below is, 3 below is fine. And specific examples of the k equals 5 situation was known to Werner in 2003. So the examples I showed you are sort of modifications of his example to do certain algebra, certain geometric things that we want. But this is the story. So that leaves 4. So what happens in 4? And it turns out that 4 is both very intricate and interesting. So in k equals 4, what happens is there are, up to combinatorics, there are 6 types of configurations, right? Because I can have 4 points in general position and 4 points in general position, like this example, or 4 in general position, 3 in a line, 3 in a line, 3 in a line, or 4 in a line, 4 in a line, and so on. So there are 6 possible combinatorial types of these 2 images. And what we can prove is that in the first 4 types, A, B, C, and D, there is unconditionally a chiral reconstruction. But in the type E and F, which is these 2 types, you can fail. So a chiral reconstruction can fail, and the result can be formulated in terms of the ranks of these points. So if you put these points in the columns of a matrix, you just compare the rank. And if the ranks are the same, then there's a chiral reconstruction, and otherwise there is not. Okay. So this result uses some interesting facts about the irreducibility of the epipolar variety, and is a little bit involved. But at the end of the day, we're able to tell what happens in all possible situations, not just generically or in general position and so on. So this is the story that happens in k equals 4. So in some sense, this is the type of question vision people like to ask. They like to know what is the threshold? So what is the value of K for which the answer goes from yes to no? And that in that sense, the answer that we've provided is complete, right? So we're saying for K equals 3, it's always good. For K equals 4, it's complicated, but here's the full story. And for K is 5, the answer is no, okay? So it can be that there are, even in general position, examples that will not have a chiral reconstruction. And then that's enough, because if you can do K equals 5 and show that there is no chiral reconstruction, then all higher values of K will also fail, because you can embed this example into higher values of K examples, and you will be able to construct things that are in general position but don't have chiral reconstructions. Okay, so this is the complete answer. And let me spend the rest of my time talking a bit more about K equals 5, because K equals 5 is the most interesting case in some sense, and this is where the cubic surfaces arise. Okay, so this is the last set of results that we proved. So in the case of K equals 5, let me go back to just recalling what was happening. So our space LP was a P3. It had 5 equations in P8, so it's a P3. It's cut by this determinant equals 0 equation. So I have a cubic surface. And generically, this cubic surface is smooth because the rank 1 variety is 4-dimensional in P8. And if I'm cutting that with a 3-dimensional plane, generically, it'll miss it. Okay, so this is smooth. And by Bottini's theorem, it's irreducible. So this is a smooth, irreducible cubic surface. Okay, so here, for example, is a picture. And not only that, it comes with a natural determinantal representation that comes with our input points, right? Because all these cubic surfaces have a determinantal representation, but in our case, there's a canonical one that comes with our input, because this space LP, which was 3-dimensional, has a basis. You can pick a basis, so let's pick one. So let me say the basis is M0, M1, M2, M3. And now, if I make this formal linear combination, M0, Z0 up to M3, Z3, then that's how any matrix on LP looks like. And if I also wanted to lie on R2, I just set the determinant equal to 0. So there is this symbolic matrix that we can write down by choosing a basis in LP that gives you a determinantal representation of this cubic surface. Okay, so it comes with this cubic determinantal representation. And it turns out that these cubic surfaces that come from vision like this, they actually have 27 real lines. Okay, so if you know cubic surfaces, you know there are 5 topological types. There are ones that come with 27 real lines, 15 real lines, 7 real lines, and then 2 types that come with 3 real lines. And ours are the ones that come with 27 real lines. So what are these 27 real lines? Well, we saw 10 of them already, right? We saw that these walls, WUI and WVJ, they form 10 of the real lines. Okay, so this is a picture with 27 real lines. So 10 of them come like that. But turns out these 10 lines, or the image pairs that we were given, point pairs that we were given, they secretly actually carry another pair of real lines. And the way you get it is like this. You take the rank 1 matrices that you get from the point pairs that we had. So look at V1, U1 transpose, rank 1 matrix, all the way up to V5, U5 transpose. These are 5 rank 1 matrices. Look at their span. Okay, so their span is 4-dimensional. The rank 1 variety is 4-dimensional. It has degree 6. So when you cut the rank 1 variety with this span, you will get 6 points. Okay, 5 of those points are here. They are V1, U1 transpose up to V5, U5 transpose. But there is a 6th rank 1 matrix, and that's V0, U0 transpose. And that gives you 2 more lines. So you make the walls of U0 and V0. So we get altogether now 12 real lines. Okay, so I will get 6 real lines that are indexed by U's and 6 real lines that are indexed by V's. And the U0, V0 just popped up from the original 5 pairs that we had. Okay, so we have 2 sets of 6 real lines, and they are very special. Okay, so they form what's called a Schläfli double 6 on this cubic surface. So by definition, what that means is you have two sets of 6 lines, and in each set, the lines are pairwise disjoint. Okay, so they're mutually skewed. They do not intersect pairwise. But if you look at a real line from the first set and a real line from the second set, so if you look at WUI and WVJ, then they intersect if and only if I is not J. Okay, so it has a very special intersection pattern. And that's exactly the definition of a Schläfli double 6. It's a set of 6 lines and 6 lines that have exactly this intersection pattern. And that's exactly the type of lines that come out of our walls from the data that we had. So that makes altogether 12 lines. And then it turns out there are 15 more lines, and these come from tritangent planes. So what happens is you take a WUI and a WVJ, they will look at the plane they span. That plane is tritangent to the cubic surface. It cuts the surface in one more line, and that gives you the other 15 real lines. So there are 27 real lines on this, all coming from the point pairs that we had in the beginning. Okay, so this is a very special situation of a cubic surface. All right. Okay, so that's a story that's happening in P8, or we've translated it to P3, but this is happening in P8. But we can also actually see what's happening in the original P2 cross P2 space, which was the epipole space that we had. So let me explain how we go from P8 to the P2 cross P2. So if I have a rank 2 matrix X, I can simply send X, which lived in P8, to its right kernel and to its left kernel. Okay, so these are unique. So I can make the map that sends X to its right kernel, which is U, and its left kernel, which is V. So these are 2 copies of P2. And the way you do it actually is just via the adjoint of the matrix. Okay, because the rank of the matrix is 2, the matrix is not invertible. So if I take X times the adjoint, I will get 0. So this means that every column of the adjoint is in the right kernel. And similarly, adjoint times X is 0. So every row of the adjoint is in the left kernel. So this is how you actually do the map. You just send X to a column of its adjoint and to the row of its adjoint. So we can map from P8 into P2 cross P2 from the rank 2 matrices. And we're going to use this map to go into P2 cross P2. Okay, so let's blow down this cubic surface. So we have this cubic surface, and you can blow it down into the 2 P2s via this adjoint map. And if you do that, on the one hand, what happens is if you blow down to the left, as I've shown here, what happens is all the U lines that were on the surface map to the U points. Okay, so I get 6 points here, which are marked with U's. They come from the U lines that were on the cubic surface. And all the V lines that were on the cubic surface map to conics. So they map to conics that go through all the U points except one. So for example, the V1 line will map to the conic that goes through all the U points except U1. Okay, so the lines map to conics, and similarly on the other side, if you blow down the other way, the V lines map to points and the U lines map to conics. Okay, so this is what happens in the blowdown. And once you have this blowdown, then we can actually see the chiral regions a little bit better. So remember, the chiral regions are up on the cubic surface, which is living in P3. But once you do the blowdown, you see that the semialgebraic regions upstairs, which were bounded by these lines or walls, are now bounded by conics. So you see these shaded regions that are bounded by conics, which we can construct. And that's exactly where the chiral regions are, meaning that if one epipole is in the 2 epipoles of your cameras have to live in the 2 shaded regions. One has to live in this gray part, and the other one has to live in the other gray part. Okay, so you can see these chiral regions in the P2 cross P2 after the blowdown. But more useful is that you don't actually need to do this construction. So one of our main theorems is that in order to test if there's a chiral region, it is actually enough to test the 20 corners that you get by intersecting an I wall and a J wall. Okay, so the I wall and the I wall will not intersect in the case of k equals 5. Remember, it's a Schläfli double 6. It doesn't intersect in the II. There's no II corner. but there are ij corners for every I and j that are different from each other. And there are 20 such, and there's a test you can do on those corners that will tell you whether there is a chiral region, whether it's adjacent to a chiral region. So this is one of our main theorems, that the test is actually just totally constant time. It's an easy test that just looks at these different corners. All right. So to finish, let me just say a moment about, talk for a few minutes about what happens if you are familiar with the usual blow-up construction of the cubic surface, right? So in classical algebraic geometry, you can construct cubic surfaces by blowing up 6 points in P2. So we could try to see what happens with that. So let's start with our 6 points, which are our U points. So 5 of the points were given to us, and remember the U0 got constructed a few slides ago. So anyway, let's assume we start with these 6 points. I've also drawn the conics because they're just conics that miss 1 point at a time. So they're here. And now you can blow up this P2 at these 6 points to get a cubic surface. So how do you do that? If you remember, what we have to do is we look at all the cubics that pass through the 6 points. There's a 4-dimensional vector space worth of it. So choose a basis for that vector space. So let's call it C0 up to C3. These are cubics. And then just send every x in P2 to C0x, C1x up to C3x. Okay, so this is a map from P2 to P3. And it is defined everywhere at these, except at these U points. So this is the blow-up construction. And under the blow-up construction, these U's, we'll call them primal base points. So once you do the blow up, these the exceptional divisors of the U points are the U walls. The strict transforms of the conics are the V walls. And there will be a natural determinantal representation that comes out of this blow up via the Hilbert-Birch matrix of the free resolution. Okay, so that's maybe not so important to know right now. But the point is that the determinantal representation depends on the cubics that you chose. Okay, so you can get a determinantal representation. And now we can blow down to the other side. So you can blow down either with the adjoint map or via another Hilbert-Birch. And if you do that, you'll get dual base points. And these dual base points are V's now. And the dual base points also depend on the cubics that we started with. So the choice of cubics here gave you the determinantal representation, which in turn gives you these V points. And what happens here is that the V points that you construct here, they're completely different depending on which cubics you choose here. So there's nothing canonical that's happening. And my point here is that chirality cannot be actually determined by knowing just one P2. So if I know one P2, that is nowhere near enough, because on the other side, you will get completely different V's each time you choose a different cubics basis, and chirality will change depending on which points you actually construct here. So this is a question we had for some time, whether one P2 actually carries all the information, and the answer is no, it doesn't. Okay, but even more dramatic things happen. So if you fix even both image points, say, let's say the U's and the V's, the U0 and the V0 came automatically, so they just get carried along. So even if you fix both sides, that means you're fixing everything, the U's, the V's, the determinantal representation, everything. Even if you do that, chirality is complicated, because what's happening is that if you pick a set of 5 points on either side, for example, I pick 1, 2, 3, 4, 5 on either side, then I will have no chiral reconstruction, which was the example we saw much earlier. But if you pick a different set of 5 points, so if I pick, say, U0, U1, U2, U3, U4, and V0, V1, V2, V3, V4, then I will suddenly have chiral regions. So chirality is complicated. It's a very arithmetic object that is not controlled by combinatorics, or even the situation that we saw before, where you have information in one P2 and the corresponding determinantal representation. So this is the story. This is what happens in k equals 5, which is, as I said, the most interesting case. K equals 4 is technical and also complete in the sense of not requiring genericity. This k equals 5 story is under genericity. Right, so that's all our results. So thank you very much.
So thank you very much, Rekha, for this wonderful talk. I have to apologize because I forgot to tell everyone to write your question on the Q&A. We wrote it on the chat, but people seem to have understood. There are 2 questions. If you have more questions, you still have the time to write your questions. So now I think I will read the questions to Rekha and give her the chance to answer. So the first question is about the points. So what if one considers the points up to renumbering?
Oh, so the numbering is actually very important, right? Because when you think of how you reconstruct from 2, I guess maybe I'm not sure exactly what the question means. It's important to match them. So it's important to say that if I have the corner of a church in this picture, I have the same corner of the church in the other picture, and they're numbered U1 and V1. So in that sense, they're important. So the pairing is important. I don't know if was the question, or you're allowed to mix up points.
That's difficult to say right now. The question was from Alicia, so we actually.
Well, we can also we could unmute Alicia at that point. Can do that.
Is that possible?
I think I did this now.
You did this now. So Alicia, you are on.
I am okay. So my question was that if you see the sets of points, but there is no obvious way how to number them, maybe the answer will depend on the way you do that. This was my question.
Yeah, so this is actually a very important pre-processing step in vision. Okay, so if you're given points, there are people who spend a lifetime trying to understand how to pair things together. So this is a matching algorithm that's usually done through combinatorial optimization. So it's very important to have a good sense of which points go with which points in practice. So of course, as a mathematical question, we can change the numbering and ask all kinds of questions. That's fine. But this pre-processing step is for us the input. But doing that pre-processing step is actually very, very non-trivial, and actually coming up with points. And some points will be mismatched, and in practice, people will throw away those points when they realize that it's not going to work, and so on. So there's a complicated pre-processing step that did the pairing.
Thank you.
Okay, next question from Matthias Himmelmann. You mentioned that the proposed algorithm works in constant time for k equals 5. Does this mean that k really is no factor when increasing the complexity of the algorithm? Okay, so
okay, I should just be very simple about it. The only thing I meant to say is that, so k is 5, okay? We're not increasing k, k is 5. In that case, we just end up having to test these 20 points. That's what I meant. So yeah, so I apologize if the meaning wasn't clear. But for these 20 points, you have to do a test, and the test is fairly simple. But if you do that, then you can tell whether it's again a type of oriented matroid test. You have to test certain determinants. You have to see if they have the same sign. And if they do, then it works. So this is very much a k equals 5 test. If you have more points, of course, you can always restrict to a subset of k and see if they have a chiral reconstruction, and if that fails, then the whole thing fails. So this is also similar to certain algorithms in vision that are called ransack, that's done where you take subsets and do tests. But for larger k's, typically these things are, the epipolar variety doesn't even exist, right? Because if you have too many point pairs, the equations are typically not satisfied. I mean, there's nothing when you take the equations, you just get an empty set, unless they're truly images.
Okay, thank you. So Timothy Duff asks, is it a coincidence that 10 is also a significant number for the problem of reconstruction from 5 points with calibrated cameras?
So for calibrated cameras, you can ask the same question again for calibrated cameras. So as I said in the beginning, it's important to fix your model of the camera to answer this question. And there are results known for calibrated cameras, and I don't think that 10 and this 10 are related, the 10 that Tim likes, but there are similar results due to, or partial results due to NIST and Shafilitsky for calibrated cameras. And it also involves some serious algebraic geometry, but we haven't gotten there yet. But yeah, no, I don't think the 10s are related.
Okay, thank you. Kathlén, you had some comments, but okay.
Oh yeah, can I ask also a question?
Of course.
So did you do you said so the result with the cubic surface and the 5 point correspondences was for the generic type of point constellations. Did you also look at like a few examples where the points are in special position, and then what would happen?
So yeah, so the original example of Werner, which we modified to those 2 examples I showed you, that is in, well, it's not exactly in special position, but the cubic surface is singular in that case. And we didn't really study all the non-generic types in those cases. There's a lot of them. So since the answer here is already no, and it's not just it's an isolated example, there's a whole, the region of bad point pairs is actually Zariski dense. So if you wiggle things a little bit, it stays bad, right? So it just seemed like, okay, yeah, we stopped there. We didn't really examine all the non-generic situations for k equals 5.
Okay, we have one more question from Christian Rannestad. With k equals 5, you may get the 2-dimensional chiral region. You get a surface of possible reconstructions. How do you choose?
Oh, which one to take? Ooh, I don't know. This may be a question for a vision person. So there might be things they like more than others. I don't know if any of my collaborators are here, if anybody wants to answer. Yeah, I don't know if I mean, they're all good technically they're all good, but there might be ones that are better than others for, is Sameer here?
Yeah, Sameer raises his hand. I will try to unmute him. Wait, I cannot. Now I allow, maybe it works now.
Can you hear me?
Yes.
Okay, so there are 2 different things that happen. I think that we should distinguish between the study of minimal problems versus how reconstructions are done in practice. So in practice, you have more than 5 points. And the reconstructions that you want are ones where the other points are also explained in some manner. The reason minimal problems of, say, k equal to 5 are interesting, there are 2 reasons for it. One is, of course, the theoretical reason where we want to understand how, what the basic mathematical theory of these reconstructions are. The second one is that they serve as, especially like the 5-point algorithm for the 2 calibrated camera case, they serve as subroutines for algorithms like RANSAC, where you're trying to do robust fitting of, you're trying to detect outliers in the matching process that Rekha talked about earlier, and find an initial reconstruction that robustly explains the observation that you have. So, but to go back to the question that was asked, usually there are more points that you have, and some property of those would be used to distinguish between the candidate reconstructions. So this is how you do it, for example, when you have 10 solutions that come out of the 5-point minimal problem for 2 calibrated cameras. Then you evaluate all 10 solutions. First, you check whether they're real or not. And if they're real, you evaluate them against the other n-5 points to see which one best explains those points.
Okay, thank you very much, Sameer. So I think these were all the questions we had. So maybe we can take the opportunity again to thank Rekha. And let me also take this opportunity to publicly thank, in fact, Kathlén, Jose, and Joachim for all the work they've done and they will do for the organization of this seminar. Thank you very much. Thank you again, Rekha, for this wonderful opening. We couldn't have done better. Thanks a lot. And I guess I hope to see you all at the next seminar, which is in about a month. Actually, Kathlén, you have the right, maybe, do you remember the right date? Because I don't, if you want to say this.
Yes, I can say this. And I also want to say that if people want to stay around for like another minutes of more informal discussion, then you can raise your hand also now at the end, and then we will promote you to panelists so we can see you and we can talk to you, and then we can do this. And so the next talk is going to be on December 8th, December 8th, by Camilla Holanti from Aalto University on coding theoretic framework for private information retrieval.
Okay.
Also, I think, yes, this is what Jose also wrote in the chat now for everyone, and also pointed out NASO talks and other related talks, the statistics seminar, and yeah, check it out.
Thank you. Okay, thanks a lot to everyone. So the first part is over now. So as Kathlén said, whoever wants to stay on is very welcome to do that.